All right, back in action. We are now starting rotational dynamics. If you got my message on the announcements, we have a quiz coming up this Thursday, and it gives you the sections to look over in preparation for that quiz, and that'll be at noon. I'm still working on the format for that quiz, and so I'll make more announcements regarding that. Please check your Canvas every day, and there'll be updates on it regarding all of these different organizational changes that we're making. All right, so with rotational dynamics, what we're interested in is looking at a problem in which an object has spatial extent, so it's not a point mass anymore, and that object has not necessarily any motion of the center of mass, but we have motion about the center of mass. And so, for example, a wheel would be an example of this. Here we have the center of mass of the wheel, and we could have the wheel rotating with a angle that we could write here as theta. So this would be a angular displacement, which would be associated, say, with this motion as we go through an angle theta. And as we all know from earlier junior high school math, S equals r theta. So here S is the arc length. So this is a distance, but it's a distance along a circular path. R is, of course, the radius. And theta is the angle measured in radians. All right, so associated then with this wheel rotating through an angle theta, it also has an arc length distance s, and s is equal to r theta, but theta must be measured in radians. We might wonder, why not degrees? Why does it have to be radians? Well, we do know that the circumference of a circle is 2 pi r. And so if that is the total distance that we travel, then this is going to be r times theta. And so therefore theta is equal to 2 pi. 2 pi what? Well, we've learned this before from our math classes, that this is in radian measure. So this is an easy way then to describe the arc length in terms of the angle, is to use units in which theta is measured in radians. Now what if we measured in degrees? Well, then to satisfy this relationship that 2 pi r equals r theta, and theta was 360 degrees, then we would have to multiply by a correction factor of 2 pi over 360. So what that means then is that S would equal R times 2 pi over 360 times theta. And so if we wanted to measure theta in degrees, we could do it, but then we would have this kind of obscure conversion factor out in front. And so that's not a natural set of units for measuring the arc length, but radians is. So what is 1 radian? Well, 1 radian is just equal to the angle that we sweep out when the arc length equals the radius. Call it angular displacement. So when the arc length distance s is equal to 1 radian, or I'm sorry, when the theta value is equal to 1 radian, the s value is equal to r. So when s equals r, then theta equals 1 radian. Okay, so how much is that? Well, 1 radian equals 57.3 degrees. Okay, and so if you take 57.3 and multiply that by 2 pi, you get 360. Okay, and so that is the way in which we would always want to convert if we had an angular quantity that was measured in degrees to get it back to radians. Or a more simple way of writing that is 2 pi radians equals 360 degrees, or pi radians equals 180 degrees. So those are useful conversion factors to get us back and forth between degrees and radians. Okay, and so that then is how we describe the angular displacement in terms of the arc length distance that is traveled. Now, what about if we were to talk about the velocity? Well, the kind of velocity that we would be talking about here would be a tangential velocity. And in circular motion, that tangential velocity is always tangent to the circular path. So let's look at the simple case that we looked at before with uniform circular motion, in which the tangential velocity was a constant. If that's the case, then as we sweep out an angle theta, we are going to have a rate of change of arc length. And so V tangential will equal d arc length dt. And so that will be equal to the derivative with respect to time of s is r theta, so it's going to be r theta, dr theta dt. We'll assume here that r remains constant as this object rotates. And so this then is first times derivative of the second plus second times derivative of the first. And so v tangential equals r d theta dt. But d theta dt is just omega, which is our angular velocity. Okay, so omega then, we could put this in our collection of relationships. Omega is d theta dt, and since v tangential is r omega, then that's also equal to v tangential over r. Okay, so omega then is our spin rate, and that's equal to the tangential velocity divided by the radius. And so what would be some omega values for different objects? Here we have the Earth. Okay, and so we have an omega for the Earth. As the Earth rotates, we have an axis that we can consider to be the direction of omega. Now, how do we get that? Well, if we go up to the data projector for a moment, we see here that v is r d omega dt, but that velocity changes as we go from one value of the radius to another, whereas the omega value stays constant, because the omega value is v over r. So if r changes, then v changes by the same amount, so that omega stays constant even though the tangential velocities would change from point to point on a rotating object. And so there is an actual directional quantity that is associated with omega, and we can consider that to be our spin axis. So in this problem then, if our radius vector goes from the point of the center of mass, the center of spin, to the point in which the object is rotating, we can say that v is equal to r cross omega. So this is a vector cross product in which what we'll do is we'll stick our arm in the direction of r and then curl our fingers in the direction of omega. So omega is our spin axis, and that goes into or out of the board, in this case into the board. So we do r cross omega, and that gives us the direction of v. So here, because omega is into the board, we would do r cross omega. V would be that way. Down here, we would do r cross omega this way. And over here, we would do r cross omega, which would be that way. And so this gives us then the relationship between the tangential velocity, r, and the direction of our spin axis. So with the Earth rotates, its spin axis points through the north and the south pole of the Earth. And so the omega for the Earth would equal, now here remember that we're talking about a total amount of angle, so that would be 2 pi radians per day. Okay, so that would be omega for the Earth, but not in the correct units of radians per second. So to get omega for the Earth, we would have to convert days into seconds. So we'd have here 1 day for every 24 hours. And then we would have 1 hour for every 3,600 seconds. So our omega then for the Earth would be 2 pi divided by 24 times 3,600. And so that would just be a fraction of a radian per second. That would be pi divided by 12 times 3,600. And so this would be a relatively small number, but this would be in units of radians per second. Similarly, we could be talking about a rotating bike tire. Let's say that this bike tire we're rotating at a rate of 60 RPM. Okay, so that means that it would be going around 60 times in a minute. Okay, that's a little too fast. Still too fast. Okay, something like that. That would be about 60 times a minute. Now, some of you that are math whizzes will immediately see that that's the same thing as 1 revolution or 1 complete rotation per second. But let's just write the whole thing out. Omega, if it's equal to 60 RPM, that is units of omega, but it's the wrong units, so that we'll write it as cycles per minute. Put a 60 in there. And then we'll convert minutes to seconds by saying that 1 minute for every 60 seconds. And so that gives us 1 cycle per second. That's still not quite right because we have to convert to radians. So that's 2 pi radians per cycle. And so that gives us 2 pi radians per second for omega. Okay, so 1 cycle per second, or 60 RPM, that's all just another way of saying 2 pi radians per second. But this is our preferred units. We want theta to be in radians, just for the same reason that we wanted arc length equals r theta. We wanted theta to be in radians there, because just differentiating that then gives us our r omega for v tangential. Okay. And so with that idea in mind, let's move ahead to angular acceleration. Now so far, what we've looked at is just kind of reframing uniform circular motion. But what makes it different now is that if you apply a torque to this system, we talked about torque in chapter 11. If I apply a torque to this system, now the omega will change. And so remember, that's what torque does. is it changes the value of omega. So let's allow then for changes in omega. We'll define alpha to be equal to d omega dt. And that'll equal our angular acceleration. Which is just simply the time derivative of omega. All right, and so let's remember then that, and we'll keep this over here so that we remember it. S equals r theta, v equals r omega. And so if we write this then as d omega dt, then that's the derivative with respect to time of v tangential over r. But again, assuming that the radius stays constant, this is just dv tangential dt divided by r. Or that's equal to our tangential acceleration divided by r. So this is vt that's equal to r omega, but at equals r alpha. And so if omega has units of radians per second, then alpha should have units of, you guessed it, radians per second squared. And so those are the units then for alpha, which now is representing a change in the spin rate. So that's, put simply, what we're talking about here is a change in the spin rate. Now, how do we get a change in the spin rate? Well, we're getting to that, but we've already had some preliminary look at torque, and so that's what does it. So torque causes alpha, which means a change in the spin rate, or a change in omega. Okay, so we want to be thinking this way, although we don't need that quite yet, because what I want to do next is set up what are called our rotational kinematics equations. And so those equations are very similar to our linear kinematics equations, with the basically the scale factor here of r. Okay, because we see that this is like displacement, this is like velocity, this is like acceleration, but along a circular path. But it's more advantageous to use theta, omega, and alpha to measure these rotational quantities, because it doesn't matter where you are on the object in terms of the radius. The theta value is the same whether you measure it here or you're measuring it there. The theta on a rigid body stays the same, whereas the displacement, the velocity, and the acceleration changes from point to point. And so it's a more natural set of units to use theta, omega, and alpha because it applies anywhere along the radius of a rigid body. And you can always convert back to arc length, displacement, tangential velocity, and tangential acceleration simply by multiplying those quantities through by r anytime you want. Okay, and so let's just review quickly the linear kinematics equations, and what we'll see is that the rotational kinematics equations are analogous. V final equals V0 plus AT. So this is linear kinematics. This is one of the first things we looked at in this class. We can also say that x equals 1/2 times v initial plus v final times t. x equals v initial t plus 1/2 at squared, and v final squared equals v0 squared plus 2ax. Now what I'm going to do, because theta is equal to s over r, omega is equal to v over r, and alpha is equal to a over r, is that very simply I'm going to imagine now that we're looking at rotational motion so that these velocities become tangential velocities, the positions become angular displacements, and the acceleration becomes angular acceleration. So if I just divide through by r at the appropriate place, what we end up with is our rotational kinematics equivalent. So here we have omega final equals omega initial plus alpha t. Here we have, well, this is x over r. So if we imagine this to be like an arc length, then this is theta. This is over r, that's over r. So this would be 1/2 times omega naught plus omega final times t. For the third equation, again dividing by r, we would get theta equals omega 0t plus 1/2 alpha t squared. And finally, in the last equation, because it involves squared quantities, we'll need to divide through each term by r squared. Here in the last term, we can spread out that r squared so that one of the r's is dividing by a and the other is dividing by x. So that gives us omega final squared equals omega initial squared plus 2 alpha theta. So these are our rotational kinematics equations. Remember that our linear kinematics equations worked if the acceleration is a constant. The rotational kinematics equations are valid if and only if alpha is a constant. And so what we'll see later is that this means that a constant torque must be applied. I haven't really established that yet, but I'm just going to state it here. And I'll justify this in a few minutes.